Hey everyone, welcome. Today we're diving into Leetcode problem 1863, sum of all subset XOR totals. It sounds a bit complex with XOR and subsets, but don't worry, we'll break it down step by step and find a surprisingly neat solution. Let's get started. Okay, so here's the task. We're given a list of numbers, called, we need to figure out all the possible subsets we can make from this list. Remember, a subset is just a smaller collection of elements from the original list, including the empty set. For each of these subsets, we calculate its XOR total. That's just the result you get when you apply the bitwise XOR operation to all the numbers in that subset. If the subset is empty, its XOR total is 0. Finally, the big goal, we need to add up all these XOR totals from all the subsets. That final sum is our answer. Let's walk through the first example. The list is just 1, 3. First, what are the subsets? Well, we have the empty set, then we have subsets with one element, 1 and 3. And finally, the subset with both elements, 1, 3. Now, let's find the XOR total for each. The empty set is 0, is just 1. 3 is just 3. For 1, 3, we calculate 1 XOR 3. In binary, that's 01 XOR 11. Which gives 10, that's 2 in decimal. So the XOR totals are 0, 1, 3, and 2. Add them all up. 0 plus 1 plus 3 plus 2 equals 6. That's our answer for this input. Let's try a slightly bigger one. 5, 1, 6. Okay, how many subsets will there be? If there are 3 numbers, there are 2 to the power of 3, which is 8 subsets. You can see them listed here. The empty set, the single numbers, the pairs, and the full set. Let's quickly check a couple of XORs. For 5, 1, 5 is 101 in binary, 1 is 001. 101 XOR 001 is 100, which is 4. For 5, 1, 6, we already know 5 XOR 1 is 4. Now, 4 XOR 6, that's 100 XOR 110, which gives 010 or 2. If you calculate all the XOR totals, D0, 5, 1, 6, 4, 3, 7, 2, and add them up, you get 28. Make sense? So, the most straightforward idea is, well, exactly what we just did manually. We could write some code, maybe using recursion, to generate every single possible subset. For each one, we calculate its XOR total and add it to a running sum. That definitely works, but think about how many subsets there are. If our input list has numbers, there are 2 to the power of n subsets. That grows really fast. Calculating the XOR for each might also take time proportional to n. So this brute force approach might be something like order n times 2 to the n. That's likely going to be way too slow. If the input list gets even moderately large, we probably need a cleverer approach. Okay, maybe generating all the subsets explicitly is the bottleneck. What if we shift our perspective? Instead of looking at whole subsets, let's look at individual bit positions. Think about the 0th bit, the rightmost one, the first bit, the second bit, and so on. Could we figure out, for a specific bit position, let's call it the bit, how many of the final subset XOR totals will actually have that specific bit set to 1? If we can figure that out for each bit position, maybe we can construct the total sum more directly. Here's the really cool part. Let's focus on one specific bit position, say the KTH bit, like the 2's place or the 4's place, etc. Now, if none of the original numbers in our input list nums have this KTH bit turned on, well then it's impossible for the XOR sum of any subset to have that bit turned on, right? XO ring, a bunch of zeros at that position just gives 0. But what if at least one number in nums does have the K-TH bit set? It turns out that in this case, exactly half of all the possible subsets will end up having the K-TH bit set in their final XOR total. Since there are 2 to the n subsets in total, that means 2 to the n-1 subsets will have this K-TH bit set. So the total value this single bit position contributes to our final sum is its place value, which is 2 to the k, or 1 less than k in code, multiplied by the number of times it appears, which is 2*n1. So how do we efficiently figure out which bit positions are present in at least one of the input numbers? The bitwise OR operation is perfect for this. If we take the bitwise OR of all the numbers in the input list, the resulting number, let's call it total_OR, will have a specific bit set to 1 if and only if that bit was set in at least one of the original numbers. Now, we know that each bit k that is set in total underscore, or contributes, 1 less than k, 2 caret, n1, to our final sum. Adding these contributions up for all set bits in total underscore, or is mathematically the exact same as simply taking the total underscore or value itself and multiplying it by 2 caret, n1. How neat is that? And here's the Python code that implements this clever OR trick. It's surprisingly short. First, we get the number of elements. If n is 0, the sum is just 0. Then, we loop through the numbers, calculating the bitwise OR of all of them and storing it in total underscore OR. Next, we calculate 2 to the power of n-1. A fast way to do this is using a bit shift, 1 less than n1. Finally, we just multiply the total underscore or by this multiplier. That's it. That gives us the sum of all subset XOR totals. Much simpler than generating all subsets, right? Let's compare the efficiency. That first idea, generating all subsets using backtracking, was really slow. Something like order n times 2 to the n time complexity, which is exponential. It also uses some memory because of the recursion calls, roughly order n space, but this optimized OR trick, it's way faster. We just loop through the list once to calculate the total OR value. That's order n time, linear time, which is fantastic. And look at the memory. We only need variables to store the count, the OR value, and the result. It doesn't depend on the size of the input list, so that's order 1 foot, or constant space complexity. Much better. So to wrap things up, the problem asked for the sum of XOR totals of all subsets. While we could generate every subset, that's usually too slow, because there are exponentially many. The breakthrough comes from thinking about each bit position separately. The crucial insight is that if a particular bit is present in any of the input numbers, it ends up being set in the XOR total of exactly half the subsets. We can efficiently find all bits that are present anywhere using the bitwise OR operation on all the input numbers. And the amazing shortcut is that the final answer is simply that total OR value multiplied by 2, raised to the power of n-1. This gives us a super efficient linear time and constant space solution. Hope the walkthrough and the OR trick explanation made sense. It's a neat example of how changing your perspective, like focusing on bits instead of subsets, can lead to a much more elegant and efficient solution. If this helped you out, feel free to hit the like button, subscribe for more Leetcode explanations, or leave a comment if you have any questions or other ways to solve it. And hey, if you're feeling extra supportive, the Boba Fund is always appreciated. Keep practicing, keep coding, and I'll see you in the next video.